So in the name of God, the title of this video is Bending Moment Diagrams. So the whole purpose of this video is to teach you how to draw bending moments diagrams and shear forces diagrams. So for example, assuming a beam, a general type of beam with general type of loadings. But the only constraint that we have, it have to be determinate. It means that the number of support reactions be equal to number of equilibrium equations. So this is the only constraint that we have for static problems, okay? So assuming this beam under a general type of loading, okay, and we do not know what is the distribution law or function that this load is obey. For example, the general form is qx, but if it's a linear, it's a parabola, it doesn't matter, okay? It really doesn't matter what type of loading you have. So it says that if I cut this beam from here or here and trying to draw the remaining parts in this way, what are the forces that must be developed in this cut that actually satisfy the equilibrium of the beam section? So what it means, it says, okay, you cut the beam, here's the loading, and you have also a support reaction force. What must be developed over here to ensure me that I have equilibrium? So that is the purpose. And in name it mx, it name it nx, and vx. You must now ask why this special type of direction that you put. In static, we have a certain sign convention that we must obey. And when I say convention, it's really a convention. We say that m is positive in this way. So if I cut in a way that the section is in right, I have to draw m according to this sign convention in a way that the upper fiber be in compression and the downward fiber over here must be in tension, okay? But what about the shear forces? The shear forces are the same. Now, why we make it like that? Because you see, if I try to get a moment equilibrium around this support, the shear force must be able to cancel out the moment, okay? So if you think about these directions, it actually makes sense. And NX are the axial forces that are not important in the beams actually when you do not have any inclined loading. So all it says is find out mx, nx, and vx according to the equilibrium equations. Concatenation of forces in x direction must be equal 0. Concatenation of forces in the y direction must be equal 0. And concatenation of the moments around certain point must be equal to 0. Can we write in a different way? Of course. There you can write sigma m around one point, sigma m around another point. But the sigma Fy or sigma concatenation of forces that you write must have certain conditions that we do not discuss it in here. So until here, we understand that there's nothing hard about it, but what make it hard is actually this resultant of forces and how mx and vx changes throughout the length of the beam. There are several ways to actually draw the bending moment diagram. One of them is by writing equilibrium. Another one is by being able to guess the general shape of the diagrams. Another type is first draw the shear force diagrams and then use the shear force diagrams to calculate the moments diagrams. So the first type that I like, and I will be doing for you today, there will be other actually watch list that I try to solve problems, but here I'm just trying to teach you the concept. So for example, assuming you have a simple supported beams with under uniform loading, one of the easiest type of loading you will see in your life. So why we actually try to teach with this simple problem is because these are basic problems that will help you in the future. Even if you try to get a PhD, you will still see that they try to teach complex problem on the simple models and make you to adapt the thinking to complex problems. So do not be, you know, tired of seeing this kind of beam and stuff like that. So this Wx and it's equal to W0. It's a uniform loading. So first of all, we try to analyze the problem. So step one is analyzing the problem. So what are the forces? Name A, named B. So here I have Ay and here I have Ax forces. Okay? And here I have a By. Sigma m around A equal to 0 leads me to know By over the length L equal to WL multiplied to L half. And I hope you know how we derive this. By will be equal to WL2, half of the amount of total force. And if you write a sigma y, you understand that By plus Ay must equal to WL. So Ay is actually equal to WL half. So next step is to draw the shear force diagram. Okay, the shear force. So if I cut the beam in a distance x from the support, here, x, here, and this is the load. Please tell me what we see here. My teacher always say, when you cut it, you will see it. And it's actually work for beams. When you cut it, you free the forces, so you will see them. Okay? Mx, Vx, and Nx. So I want to find Vx, so I write the concatenation of forces in the y direction. So I have WL half in the upside. I have a minus Vx in the downside, and I have minus Wx equal to 0. So Vx is actually equal to, let me write it here, Vx is WL2 minus Wx. What it means is, because the load is uniform, it will vary linearly, okay, like this. And here, when I put 0, you get half of the WL, so it's positive. Where this positive and negative come from is actually based on this. If the shear force that you calculated have the same direction at the signing convention, it's positive. But if it has a negative opposite direction of your sign convention, it must be negative. Look at this shear force diagram. Okay, at 0 you have your force Ry, support reactions. What is this amount? Is half of the WL, and you have it. Then when you go in x directions, there are little forces in the same direction as Vx, based on the sign convention that we had. They trying to weaken the bond here, okay? They, in the opposite side, they try to make shear force weaker and weaker. The thing is, you think now, this the loading has the same direction as the shear forces, okay? But think about it. When it has the same direction as the shear forces, it causes the amount of V or shear force decrease, okay? And in here, it says I am equal to the amount of the support reaction. And then from here, if you pass the half of the beam, it says shear force actually says, okay, the support reaction is gone, and now I get forces downward. So I cannot be in the same direction as a sign convention that we had. I need to be upward to actually can cancel out the forces. And you see, because shear forces directions change and it's upward, we get a negative amount. And we go to L, x equal L. And you see support reaction By equal to half of the WL, cancel out, and we reach here, equilibrium. So equilibrium must be seen in bending moments diagrams, in shear force diagrams, in every one of them. Next, we try to write the bending moment diagram. Next. So, if I write it here and now trying to draw the bending. There are two ways of thinking here. I do not want to make you think about integrals and differentiations. We will in the next episodes, but now the only thing I want to think about is cutting the sections, writing equilibriums. Okay, I want you to do this way until you master it, and then you can go to solve it with other ways that I will teach you actually. I'm very good at statics, and the only reason is because I had a very hard, very how can I say it, good teacher. He probably, when I was a bachelor degree student, I I didn't like him a lot, but he actually helped me a lot. He failed me on my statics course actually, the first time, and he told me the static is the gate of engineering. and I do not let you pass it without the proper knowledge. So in a way, I am owe him a lot. So I hope what I've been through doesn't happen to you guys, and pass the statics and other solid mechanics courses very easily. So here again, we cut it. When we cut it, we have x directions, we have vx directions, and we have nx directions. Now, again, we have equilibrium equations. This time, concatenation of the moments around A, for example. Does it make sense? What happens if you write the concatenation of moments around point A? You cause riding shear force in your equilibrium equations, and we do not like that. This guy sucks. So write the concatenation of moments around the section you have made. So this way, and I see mx in the direction. I have some positive mx and a positive moment with, according to the loading, multiplied by x half minus. So first of all, the load was uniform. The shear force was linear. So the moment is a parabola. And its amount is mx wl2 half x minus wx2 half. Okay, now look at this. Can you draw it based on this without any calculations? Of course, it has a lot of information. First of all, it says when you start your parabola, it have a positive slope. So it must be like this. Second thing is the curve direction. You are negative here, so you know the hands are downward. So it says we have a maximum moment somewhere. So you know where we can find the maximum moments or any maximum minimum values of functions? We set the differentiation of that function equal to 0. So if I differentiate it in respect to x, I get that's the same thing that we had, shear force equilibrium. And where does the shear force was equal to 0? 0 at x equal to half of the L. So here it gets max, and then we have this, but with negative slope or positive slope? With a negative slope. You say why? Now we have something like, okay, I was very bad try. No. We try to be very patient and draw the bending. What is this amount? And memorize this one because it's a very, very, very famous number. Okay. There will be a certain point of time in this channel that we will discuss something called the plastic methods. And when we are starting that will actually be way ahead of this time. Okay, actually 2 or 3 years from now. Or maybe sooner or later. We will see if we actually have a lot of subscription and comments that wants the plastic method sooner. But first, we must end the static. So This is a famous number, and I hope you memorize it, or actually do not memorize it, you just learned it. It's not a very hard thing. But we learned something else, that V has some connection with M. And what is this connection? That if I try to derivate M with respect of X, I get V. Fun fact, if you derivate V with respect of X, you will Qx minus Qx. You're loading. Why minus? Why minus Qx? Think about it. Why minus? Why not Qx? So it's actually not a weird thing, but it's the way you draw the diagrams that define this minus. If you put the positive upside and the negative downside, you must have this minus to things add up correctly. But if you have a way of showing positive moments in below the line and negative upward, that some of the engineers will do it because they are very actually easier for in technical works. We do that actually. Do you know why? Because if you pass the concrete course, you understand when you have a negative, you put the bars on the upper fibers. We call them negatives, and it will be here. So they say, okay, let's draw diagrams in a way that shows the position of the tension bars. Okay, so for that, sometimes we try to draw the bending moments in like this and call this positive. And for that, you have to say Qx. So the only reason is that, and it's not a matter, it's not important at all. So sorry for my bad English, and I hope you learn something from this video. I do not know. And have a good night.